I want to say a few words today about something in linear algebra called the wedge product and how this relates to the determinant of a matrix. Now, if you've taken a linear algebra course, you've probably seen determinants before. They're very important, very useful things. And of course, you probably know how to calculate them, right? So if I give you a matrix, you know how to calculate the determinant of that matrix. And basically, you start off by, well, you take, a row and a column, you pick the entry there, you multiply that by the determinant of the remaining minor of the matrix, and you keep on going like this. It's a rather lengthy process. It's not anything that's particularly difficult, but there's a lot of steps of arithmetic involved. Another way of thinking about it is that if I give you a matrix, you are basically multiplying together all of the different permutations of choices of rows and columns, where you only choose one element of each row and each column, and then that particular contribution to the sum gets a negative sign or a positive sign based upon whether it's an odd permutation or an even permutation. Basically, if you have not seen determinants before, then I'm not going to say too much about them here, about how you actually calculate them. I'm going to assume that you've already seen them. So if you haven't, maybe take a few minutes to look up how you calculate determinants, how they're defined, and all that sort of thing. But the way that they are defined is kind of weird when you just see the computational definition. And so I want to show you a way in which the determinant naturally arises as a property of a linear operator on a vector space with no reference to matrices at all. We will come back to why does this thing happen to equal the determinant, but I want to explain how you can do this without talking about a matrix. If I just gave you a linear operator, what is the determinant of that linear operator really telling you? See, it turns out that all of these things in linear algebra, they have what are called coordinate-free definitions. In other words, we can define these things in linear algebra, things like the determinant, without having to talk about a basis and a matrix representation of that operator. And in my opinion, that is a much more elegant way to think about them, even though if you're just doing computations, it's probably easier to say, okay, let's write down a matrix representation and just compute the determinant that way. That's something that's easy to program into a computer, and you can do it quite quickly. Now, in order to discuss this, though, we first need to talk about what is a wedge product. So, wedge products are defined in the following way. Suppose that I have some vector space V. Then the wedge product, which also kind of is written by using a V, except it is upside down. We define the space V wedge V to be the linear space generated by stuff of the form V wedge W, where V and W are both elements of the original vector space V, subject to the following relations. First of all, we want taking the wedge of two vectors to be a linear process. So we want to say that A wedged with B plus C is equal to A wedge B plus A wedge C. And another property that we want to have here is that A wedge B should be equal to negative B wedge A. I've managed to knock down my back end of my writing implement here, so sorry about that. It turns out that this wedge product and the resulting space is part of a more general construction involving what are called tensor products, and you can think of the wedge product as giving you a totally antisymmetric part of V tensored with itself. But for our purposes, we really just want to think about this wedge product. Now, the wedge product is actually somewhat related to things like the cross product, for example. So if you actually take the wedge product of two three-dimensional vectors, what you end up with is going to look almost identical to the cross product, except that instead of having an actual cross product as a vector, what you will get is you will get something that is proportional to I wedge j plus something times j wedge k plus something times k wedge I. And to translate back and forth between this resulting wedge product of the vectors and between our usual cross product, you have to have some way of translating between these I wedge j and the usual vectors in the vector space. But in any case, it's a nice little exercise to work out how that works out. Why is the wedge product of two three-dimensional vectors basically a cross product? And in that sense, you can kind of think of the wedge product as a generalization of the cross product that works in any dimension. Now, once I have the wedge product of two vector spaces, we can actually continue to build more and more wedge products. So instead of just thinking about V wedged with itself, I can think of V wedged with V wedged with V again. In other words, I wedge together three copies of this vector space. I could do the same thing where I take a wedge product from 1 up to 4 of V. This is just like summation notation. It means that I'm taking V wedged with V, wedged with V, wedged with V, so there are 4 copies, 1 through 4. Now, the dimensions of these things are going to follow an interesting pattern, and I will leave it to you guys to sort of think about what are the dimensions going to be. But the Pascal's triangle shows up in here in an interesting kind of, well, it's not exactly Pascal's triangle, but it's a somewhat similar kind of idea. Now, one of the things that you will notice is that if V is an n-dimensional vector space, then if I take the wedge from I equals 1 up to n of V, in other words, if I wedge this thing with itself n times, then this is going to have, well, everything m here is proportional to the only way that I can get a wedge here out of the basis for V is going to be if I choose every single basis vector. So the only question is, how do I permute them? But remember that by flipping the permutation, I just flip the sign. So it turns out that everything in this wedge product is proportional to E1 wedged with E2 wedged with all the way out to En, if the EI's here are a basis for V. And because of this, in other words, this is a one-dimensional vector space. And I will leave it to you to check the details here and make sure that you understand what's going on there. It's maybe a little bit weird to think of the first time around, but the basic idea is that because wedging is linear, I only need to think about a basis for V. I can write everything in terms of a basis, and since the wedge operation is linear, it's okay to just write everything in terms of the basis. And secondly, the only n wedges involving the basis that end up being non-zero have to be something like this, where we have every single one of the basis vectors chosen. And the reason for that is because of the fact that A wedge B equals negative B wedge A. Well, this implies that any vector wedged with itself must be equal to 0. In other words, that is the 0 vector, because we have to have the A wedge A equals negative A wedge A. There's only one element of a vector space for which that is true. So this turns out to be a one-dimensional vector space. Now, we still haven't said anything about determinants, but we are getting closer. So notice the following fact. Suppose that T, taking V to itself, is a linear operator. So just a standard linear operator. As we know, linear operators, sorry, there was a little smudge there over the T, making it look funny. As we know, linear operators are basically representable by matrices. So you can think of this as a matrix acting on a vector space if you want to. It's best, of course, if eventually you can kind of think, without necessarily talking about the matrix immediately, just think of this as a linear operator. But if you want a concrete example in mind, think of a matrix and, Rn or something like that. Now, I claim that we can use T. T is also, it's not just a linear operator from V to V. It induces, which I cannot spell for some reason, a map T wedge T taking V wedge V to V wedge V. And how does it do this? Well, the idea is that it is going to take A wedged with B, and it's going to send it to TA wedged with TB. In other words, we just apply the linear operator to each piece of the vector separately, and then we wedge the results. Because the wedge operation and T are linear, you can check that all of this actually makes sense, that everything we do here, there are no issues involved. There's no ambiguity, there's no way that you can get some kind of confusing or some kind of contradictory definition here. And in the same way, we could define T wedge T wedge T, which is going to take V wedge V wedge V to V wedge V wedge V. Sorry, my wedges are getting kind of messy here because having to write wedge over and over again gets kind of monotonous. As you can probably guess, the way that we would define this is that A wedge B wedge C should get sent to TA wedge TB wedge TC. Okay, so we're kind of getting somewhere here with these definitions, but where does the determinant come in? Well, the determinant comes in the following way. We can define, in the same way as we just did, we can define the wedge from I equals 1 up to n of T. This is going to be a map on the wedge from I equals 1 up to n on V to the wedge from I equals 1 up to n on V. But here is the key point. This is a linear operator on a one-dimensional vector space. What is a linear operator on a one-dimensional vector space? This is sort of a trick question because the answer is really, really simple. A linear operator on a one-dimensional vector space can do exactly one thing. It can scale. All it can do, you've only got one dimension. The only thing that I can do is I can stretch or shrink along that one dimension. There cannot be any rotation. There can be nothing else. In other words, this is effectively, in some sense, a scalar. And it turns out that this is the determinant. This is literally just the determinant of T. So, to be more precise, what we can say here is that the wedge from I equals 1 up to n on T, acting on the wedge from I equals 1 up to n on the EI, I should use J there just so I'm not doubling up my indices. This is equal to the determinant of T times the wedge from I equals 1 up to n of EI. So we scale everything by the determinant. Now, how does this relate to the usual definition of determinant that you know, the one that involves calculating things with the minors of the matrix and all that? Well, the way that you get that formula is by calculating what does this actually do. So, I'm going to sketch for you where this comes from. Remember, this would be defined to be equal to the wedge from I equals 1 up to n of t acting on EI. Now, if you've watched my previous videos, you know that t acting on EI, if we represent this using a matrix, TEI is just going to be the ith column of the matrix. So the ith basis vector gets sent to the ith column in that matrix. But then what happens when you take the wedge product? Well, to get the wedge product, you have to take one entry from each of the vectors. That's one entry from each column. You can never take the same entry from two vectors because then this would give you a 0. And you add a plus or a minus factor based upon whether you've taken an even or an odd permutation of entries. But that's actually, when you think about that written out, when you write out these t e sub I in a matrix, that's literally just the definition of the determinant. You think of the determinant, you take something from each column, it has to come from a different row, and whether the rows are chosen to be an even or an odd permutation determines whether it gives you a plus or a minus. So that formula for calculating the determinant is exactly what you get when you do this definition. So why would you care about this definition? Well, to reiterate, the reason that I care about this definition is because I don't necessarily want to think about things in terms of a specific basis and a matrix, right? I don't necessarily want to have to specify a basis. I don't necessarily want to represent my linear operators as matrices. There are very good reasons to do so. A lot of times it's useful to do it, especially if you're doing calculations, if you're doing something with like computer programming, then it's usually a good idea to have an explicit basis chosen and represent your matrices, represent your operators with matrices. Okay. But what if you're a mathematician who wants to know general facts about vector spaces and linear operators? It can often be easier to see facts about linear spaces and linear operators when you kind of think of them more abstractly. So yes, this is an abstract way of thinking, but it can actually end up being a simpler way of kind of bringing all your important information into one place. Here's one good application. The fact that the determinant does not depend upon the choice of matrix to represent the linear operator. That seems really, really weird when you first think about it. Why should that be? I mean, you can prove it. One way of proving it is you prove that basically the determinant definition in terms of, the minors or in terms of picking out different elements from the rows and columns doesn't change as you change your basis, right? A change of basis amounts to conjugating the matrix. You can prove that this rather complicated definition doesn't change under conjugation. Okay, that's great. The problem with it is that it's, one, requires you to do an awful lot of annoying arithmetic. It's not hard. It's not easy. It's just kind of annoying and long to do that. That's why I'm not writing it up here, because I'm lazy. I don't feel like doing that. The second problem is it's not very enlightening. I mean, it tells you that, yes, this determinant definition is independent of basis. Okay, great. We happen to have written down this crazy definition where we pick things from each row and column, multiply them together, add and subtract, and it happens to not depend upon the basis. Well, why on earth would anybody have thought to do that, right? If we had nothing more to go on, if we had somehow like crash landed as teenagers off on some desert island, and as you do, you try to rederive all of mathematics while you wait for rescue, why would we have ever thought to do that? Well, this is the answer. This is where the determinant comes from. It is what happens when you take your linear operator and you look at the induced linear map on this n wedge of the vector space with itself. And so the determinant, which when you first see it seems like, hey, that's a cool trick, but why on earth did anybody think of this trick? Well, because it's actually very natural when you start thinking about these abstract properties. And then once you understand where the abstract property comes from, you can then say, oh yeah, and that's, this agrees with that formula, and that means that formula can't depend upon the basis, because everything I did here, this definition has nothing to do with the basis. I just figured out that once I've defined this operator, I can calculate it in terms of a basis, but it didn't matter which basis I picked. I didn't tell you which basis. So now we get for free that, the standard definition of the determinant is independent of basis. The other thing that we get is that we understand what the determinant is without even thinking about a basis. And we understand what it's really telling us. It's telling us something about what happens with this wedge. Here's one really practical impact of this. Now, something that I didn't say about these wedge products, because this is a short video, this is not an in-depth class, right? But something that you should know about these wedge products is that they basically tell you something about volumes inside the vector space. So an element of this wedge product basically tells you the volume of the, what do you call these things? The regular n-gon, not n-gons, but like in 2 dimensions, right? I could have 2 vectors, and the wedge product would effectively give me the area of this thing between them. In 3 dimensions, if I took 3 vectors, I would get something that is very much more difficult to draw, but looks like a smushed cube, basically, and it would tell me the volume. Well, effectively, what this thing tells you is how does T act on a standard volume inside your vector space. In other words, it tells you what happens with the volumes. And if you've seen the formulas for how do you change coordinates when you're doing multivariable calculus, well, effectively you change coordinates. When you change the coordinates, the volume differential, the dV, picks up a determinant of T, and this is why. So this makes it very clear why the determinant pops up in calculus once you understand that this is actually representing volumes and all that sort of thing. Normally, when we tell you that, we just kind of either gloss over why this is true, or you give some kind of complicated, basically a brute force, here's the arithmetic and it happens to work out kind of approach. But if you understand things on this abstract level, then it becomes immediate that this is what you should get. So this is why thinking about things abstractly is so powerful. All of these formulas that seem to come out of nowhere, they really come out of these, I don't want to say elementary, but they become almost obvious once you understand the power of this abstract way of thinking. Anyway, I feel like this was one of my more quick glossing over things kinds of videos here, so hopefully you guys got something out of that. If you want to know more about basic wedge products and also a bunch of other things in mathematics, introduced in a way that's not too difficult, then I recommend a book called Gauge Fields, Knots, and Gravity, and the author is John Baez, and there's a couple of other authors whose names I cannot unfortunately remember off the top of my head, and I don't see the book next to me to look it up. So the point is, if you put this in and you put in Baez's name, you'll find it, no problem. He goes into lots of different types of mathematics, including my own specialization of knot theory, and he does it in a way that's accessible to almost anybody who's had a couple semesters of calculus. He also will talk to you about, by the way, why these wedge products end up showing up in terms of integrals, because it turns out that those differentials of area and volume and things, yeah, those are actually these wedge product type things that you're talking about there. But anyway, if you want more information, I will refer you to that book.